Hi girls, so this video is about piecemeal functions. Sometimes they're also called piecewise functions. And here's an example. So let's say I've got fx equals two different things. So it equals x if x is bigger than 1, and it equals 1 if x is less than 1. Okay, so let's draw that. So we've got our axes. And basically we split the axes into two regions. The region bigger than 1, the region less than 1. So when it's less than 1, the curve is always 1. So that gives us a horizontal line through here at 1. When it's bigger than 1, the curve is x. So that would be this curve, which I'll try and draw dotted. But it's only counted when x is bigger than 1. So that means it's just this section here that's thick. And so that is the full piecemeal function for this particular fx. And then from here we might be asked to evaluate. So, we might be asked to evaluate f of 7. So then we go, alright, where does 7 land? Well, 7 is bigger than 1, so 7 lands there. So we replace x with 7, so it's just 7. And then we might be asked to evaluate, I don't know, f of 0. 0 lands here, it's less than 1, and the function is identically 1 for anything less than 1, so f of 0 must be 1. Okay. Let's do another example. Let's say that fx, oops, I'm in red now, oh well, equals x plus 2 for x greater than or equal to 0. Should have the word if there, but whatever. And x squared if x is less than 0. And let's draw. So we break our curve when x is 0, so that's the y-axis. So when it's bigger than 0, it equals the line x plus 2. So it looks like that. And when it's 0 and below, it looks like x squared. So it looks like that, half a parabola. That should hit the origin, sorry. Now there's one other thing that we need to notice here, and that is that they do not meet. So in the one we had before, I'll go back, you can see that they met at their boundary. This one does not meet. So what we need to do is we need to consider which value. What do we take when x is 0? Well, when x is 0, the curve says to evaluate x plus 2. So that's the line. So that means we don't evaluate the parabola, which means there is an open circle there. And obviously it doesn't need to be that big, but we draw an open circle there, and we could even emphasize it a little bit and draw a closed circle here to indicate that at that point of discontinuity, basically where I lift my pen from the page, at that point of discontinuity we go with the closed circle, not the open circle. Okay. Again, we might be asked to evaluate, so we could evaluate f of 0 just to reinforce that point. So at 0, it must be on the top curve, so it must be 0 plus 2, so it must be 2. F of minus 3, well, minus 3 is less than 0, so it must be minus 3 squared, so it must be 9. And then we could be asked to evaluate f of a squared. Now, this one's a little bit tricky. A squared, because it's a squared number, must be positive, so it must lie in the top one. So we replace x with a squared in the top one, so it must be a squared plus 2. And that's basically piecemeal functions. I want to talk very quickly about odd and even functions as well. So firstly we'll talk about even functions. The definition of an even function is that if I take f at negative x, it's the same as, sorry, that's wrong. It is the same as fx. Now what that means visually is if I draw some kind of curve over here on the right, and then I try to evaluate it on the negative side, which is what this is saying, then it should be exactly the same value as it is on the positive side, which means it should be exactly symmetrical, something like that, around the y-axis. And you can use those two definitions interchangeably, as long as you have a good drawing, obviously. So, for example, let's say we've got f of x is x to the 4 minus x squared plus 7, and we want to prove that it's even. Well, we evaluate f of minus x, like that, and then obviously when we raise anything to the power of 4 it becomes positive, so that's x to the 4. Same with squaring, becomes positive, and that is fx. So that is even. Now in reality what we'll end up doing is we will use this to sketch the curve. We'll have the curve, we'll sketch the positive side, and then we'll use symmetry to sketch the negative. It's a day later. I got really distracted by Porsche, so sorry if this sounds odd. And what a lead-in. Now we're talking about odd functions. So odd functions are similar to even functions, except that f of minus x equals minus f of x. So even functions it was plus f of x, odd functions it's minus. And just to point something out, this is the same as if I make it minus f of minus x equals f of x. And I'll give you an example. So the most common example that you'll see is y is x cubed, and I should have used fx, shouldn't I? But anyway, so in this case f of minus x equals minus x all cubed, which equals minus x cubed, which equals minus f of x. If you look at a graph, so let's just look at x cubed first. So this is x cubed. Now think about the symmetry for a minute, and you can hopefully see that it is a rotation around the x-axis. Sorry, not around the x-axis, around the origin. So if you take this curve here, and it's going to be bad because I've not done a good drawing, and you rotate just that section 180 degrees, you get this. So for that reason we say that this is the symmetry here is around the origin, because if I take the full curve even, if I take the full curve and you imagine it as like a, I don't know, a stick of a piece of paper that you cut out or something, and you spin the whole thing 180 degrees, it will overlap where it was before. Just for your edification, another example is just like y equals x, right? So if I take f of minus x, I get minus x, which is minus f of x. And I'll just squeeze it in here. If you think about what that looks like, it's just a straight line through the origin, apparently. And if you spin it 180 degrees, it gets back to where it started. Okay, that's odd and even functions. That'll do for today, and I'll see you in class tomorrow to talk more about it. Bye-bye.